go. So, friends, I welcome all you to this wonderful tutorial on Riemannian hypothesis. So, our views have just gone up. So, it has just gone to 100 views or 50 views on separate videos. So, today, every audience and subscribers has been asking me about actually Riemannian hypothesis actually has that the character of conformality, okay, in it. So how could you just explain it in a way so clearly plotting the zeros, because that was not clear in the way what we have explained, because we just showed the how to conformally plotting. Actually we don't know that whether it is conformal. Okay, then let me take you to a very bizarre and a very very awkward journey. Okay, it will be very awkward journey into this so-called Riemannian hypothesis. Okay, how does conformality? Actually, you are thinking that conformal is a very general one because they teach you in books and everything, but conformality is not a general one, and it is not a thing. It is a very bizarre thing because preserving areas and angles are nearly different. So let me come to the point in a very simple manner. At the end of this tutorial, I'm going to throw chaos at you. Okay, the chaos would be, I'm going to confuse you a bit on the concept of conformality and non-conformality and this Riemannian hypothesis plotting about these zeros. So let me get to you straight. So you have a complex function in this manner, z power 4. Let's have z power 4. We can't solve more than that. Okay, let's go for z power 8 plus 56 into z plus 67 into z power 7 plus 78 into z power 6 minus 45 into z power. I'm just getting very bizarre with you because I need a very complex equation to deal with. So z power 5 plus 123 into z, these are all complex variables, plus 67 into z cube and 4456 into z squared minus, you have 67 sorry 56 into z, so it will be a real number in this manner. So you have a very complex function like this, and what I'm going to do is I'm just going to substitute in a manner that this z consists of an complex variable x plus percentage I. What does this percentage mean is that in maxima it just means that it's just a complex number, the maxima syntax is of that sort. Then we just substitute, it just transforms into this. So now what I'm going to do is I'm going to just simplify, go to the complex variables. To manipulate with hand or an analytical substitution will take a long, so we use an computer algebra system. So you just get a very awkward equation like this, and this is the real part, and you just get here and you just go to the complex simplification and you get the imaginary part. Okay dear, what is this? What is this? What is this so complex? I could not understand anything. And what does this have to do with a normal thing? Okay, let me show you what is conformality and what is not conformality, and how does this relate to this so-called Riemannian hypothesis and the strip function. Okay, the strip which consists of the zeros. So I just got an wonderful software called this Explore Math 3D. Okay, I just got this software called Explore Math 3D, and it consists of conformal mapping. You just go here and you just go to conformal maps. You just click it and you just can see a very good kind of animation on this sort. So let me show you this morphing characteristics. Can you understand a bit of this conformality or non-conformality? You could not. So let me show you what is non-conformal. Okay, this is non-conformal. So it doesn't, what does this mean? So this means So you have a point over here, and you have the same point is mapped over here with some deformations, and you have to note that this angle what it preserves is not being preserved over here. Suppose this is 90 degrees. Okay, this is 90 degrees. This could be 45 degrees. Okay, and okay, so the angles is not preserved. So what could be the non-conformal mapping? um, Wait a minute. So what could be the non-conformal mapping formula for that? So it is just simple that it is conjugate of z plus a into z squared. So it is conjugate of z into a into z squared. Okay, dear, I could not understand this. What if we morph this? It just turns into a very different one. Okay, okay, dear. Then what about, let's do some circle plotting or something. So I'm just doing a circle plotting. It just turns into an oval like this sort. Okay, let me plot a little big circle now. So let's see what happens. So it just turns into a triangle. Oh my God. And let me go for a larger one. Okay, let me go for a larger one. And it nearly turns into an asteroid. So in between these things, you have an you can fine tune this to have an triangle. Okay, you can just fine tune this to have a triangle. What if the circle goes very big? So this is just some bizarre equation with non-conformality. It just turns into this sort. What if I just plot a line? What will happen? So these are the things. So it just turns into a parabola. So what something over here turns into something bizarre over there. So let me show you one Riemannian hypersphere thing. So I have told many things about this Riemannian hypersphere. Okay. So whatever you do know, it is being plotted from point of infinity to the plane of complex numbers. So let me get over here. Why I'm going very slow is, so let me show you what is the Riemannian sphere. So okay. Riemannian. So if you just watch this carefully, sphere, sphere. Okay, so you just go here. This is the Riemannian sphere, and you have a point being plotted from the point of infinity. Okay, this is nothing, just this is this grid is being plotted in a manner that it is being deformed. So when I just morph it, you can see that the morphing takes place. This is the 3D perspective of what you see. Okay, when a non-conformal mapping is being cyclically morphed, you can see that it is being very bizarre transformation is happening. When you just take a view from here, okay, you just take a view from here, you just cyclic morph it, okay, and you can see this doesn't show you the totality of this. So this is the actual thing. So it is being point from the point of infinity to the point in the complex plane. Okay, dear, let's come back to this. So it just transforms into this. So how can I understand this in any way? So I just show you another graph. So you have two planes. So this is the imaginary part, this is the UV plane, and this is the XY as it is this is the X plus percentage IY plane. So I just copy the whole formula. Okay, dear. I just copy the whole formula. Let me come there. Wait a minute. So I'm just copying the whole formula and I'm just plotting it over here. Okay. So let me get there. So this is the thing. So just I'm plotting it over there, and in here there will be some mistakes because you have some division symbol being shown over there. So you should take all those things and plot it in a clear manner. So I will show you the 3D perspective of this. Okay, that's fun. That's really fun. So you have an sort of uh, equation like this. Okay, so you just see this and you can see a lot of things. And what about the rotation or the transformation that is really happening? Okay, so these are the things what you see. Okay, real and this is real part and this is the imaginary part. Okay, slice of imaginary would be like this. Okay, I'm just showing the slice of imaginary. So this is in this axis you'll have that. Okay, this could be the slice of imaginary. So I'm just plotting you in a manner. I'm just showing you the part. So just let's see into the bizarre world of complex numbers. Okay, so this is the normal one. Okay, then what happens when we just plot this? Is it power 8? What would be the thing? Or is it squared? What would be the complex number of the sort? You have a very bizarre characteristics. So you have an sort of very in a complex domain. You just travel in a UV plane. You have an z axis which is explicitly defined in this manner. Okay, it is explicitly defined as z is equal to x squared y. Okay, so if you just can have a very high grid view, or you can take r theta view to view all these things. Okay, so this is the r theta view. Okay, this is the r theta is nothing but you are going to plot everything in the means of r and theta, radius and theta. Okay, so let me show you the another thing. So when we just plot this, you have an wonderful curve like this. You have a wonderful curve like this, or a circle which is being plotted in this manner. Okay, so let me take you to the real transformation, and so this I'll get you to this point. So when you just go up, when the line just travels up, it just forms some, a parabola becomes big. If just goes down, the parabola becomes small. This is just that the line in this manner, you just go here, you just plot a line over here, you just plot a line, it just transform into a some other curve over here. So you just can see this very clearly. So it just forms. Not only for this, you just take an arbitrary formula like this. Okay, and what you do is you just draw a line over here, and it just transforms into a some other formula like this. Okay, now what I do is I am just plotting the complex variable thing. So it is very difficult to plot the zeta function. Okay, zeta function is really very hard to plot. So when I just travel up, when you just go for here rectangle grid, and let me show you in a manner that you understand. Okay, in a very easy manner that you understand. You have z squared. We don't want to go very complex. Okay, we just don't want to go very complex, and you just plot this, and you just go to this line, and you just go up and down. When the line travels up and down, you can see that parabola is being when it just scales up, there is nothing. When it goes right to left, is just equivalent to up and down. When you take this so-called rectangle in a manner, that rectangle, what happens we will see. Okay, we'll see. So you have a grid like this. You have a grid like this on rectangular grid. Okay, this you can see here. Okay, z square. When you just move, it just converges at a point. It just converges at a point when you just travel up and down, and when you just travel down, it uh, just cyclically morphs. So let me show you another example over here. So this is another example what you can see. So you have exponential function exp power is exp, that is exponential power n in z, n power n z. Then you just move in a direction, you can just see how this just converges and diverges. When I just move from here to here, it converges. So this means that this region is where this points converges, this grid of points converges. No matter you travel to any other point beyond infinity, this would converge. When you travel here, it just diverge. Let me take another instance in sine. Okay, you can see here, when we travel from right to left, it converges and diverges, and harmonically. Okay, it just converges and diverges. So these are all nothing but these are all just the conformality mappings. So then we just go from cosine, you just have this. Okay, so what does this have to do with Riemannian sphere and Riemann zeta function and Riemannian hypothesis? I will be telling you in a very slow manner so that you can understand. So this tangent, what you are seeing here, tangent, it is just very random. Okay, tan of z. So let me show you this tan of z, how it is being plotted. So tan tan of z. Okay, I'm just plotting it. Okay, no brackets. So you just have to close with these brackets, and you can see some wonderful animations over here. So you can see it is being transformed in a way that when you just travel up and down, the grid is being transformed. You just take an elliptical grid, the grid will be transformed in some other way. So when you just zoom it, with a lot of grid points, 100 for 100, so with 100 for 100, so it's not needed, I think so, only up to 250 is sufficient. Okay, so you just have to go from here to 250 to 250, and you will have a lot of grid points. And when you just travel from here, it just transforms into one very bizarre one. This is an elliptical grid oriented thing. You have an ellipse and all those things form in this manner. So when you just travel in a way, when the grid travels from up to down, it is of this manner. Okay, you can see that in a clear thing. Okay, so these are the details so far I can give you. So these are the details so far I can give you on this conformality and non-conformal mapping. Or when you just take the surface, okay, you just take the slice of the surface in a complex domain, you have like this. Okay, so or a line, so you have a line over here, and when you move up and down, you have some sort of deformations like this. Okay, this is about tan z. Okay, this is about tan z. And let me show you another example. So these are all some examples of, so this is about power. So you have a power function, and the power function, what you can see here is, when I plot this, you can see that it is equal in all directions. It's equal in all directions. And when you go to a logarithmic functions, I think it oscillates. So it is nearly near the grid functions. It just spreads out in a manner, and it just converges when you just go to any point to infinity in either directions. In either directions you go, it transforms, goes into infinity. And also for the tangent, and for tangent it doesn't converge, but it just has a random way of spreading over everywhere. Okay, so far I have dealt with these things, and I have shown you about these spaces, complex topological spaces. Okay, so everything is a topological space where you can see this. Okay, so you have this z cube. So these also have an sort of lots of explanations in it. Okay, so let me close everything and show you. So these are the some of the bizarre things I can show you, tell you about the complex number. So let me get to a straight point over here. So it is almost 18 minutes. So this tutorial will take a very long time. So you have an function like this, and you need to show whether you need to show that this function, okay, so called this function, you copy this and you just take here, go to user conformal or map, and you just plot this over here. Okay, you just plot this over here. And please make note that you have to take this division symbols, which thinks it is an mathml script. So you just take this division symbol and you just plot this over here. So in this millennium problem, what effect does this have over this? So you, in order to take some actions of this, you just, so it doesn't have any implications over this. So I think this is enough of this. Now you can just plot any grid over here. Let me show you one sample. Not only this function, any function you can have. So for example, you have a function like this, z power 5 plus 56 into z minus 78. Okay, 778. And what I'm doing is that substitute, I'm going to insert an equation of circle into that. So for example, I am plotting in cyclic grid. Okay, I'm just plotting in cyclic grid. So for example, you just take this Argand map, okay, and you just get over here, close this, and you just get over here and just plot this. Okay, let me plot this function z phi plus 56 into z, I think minus 778, minus 778. Okay, let's see the grid. So when you just travel into the space of these complex functions, it is so bizarre. It is so bizarre that I am just lost in this. I am just lost in this. I could not find my way out. Okay, right. So let me show you the circle grid. Okay, this is the circle grid. And when you just go small, there is nothing over here. When you just go big, there is nothing over here. So what about this rectangular grids? So I think we are misled now. We are really misled now. So let me go for an 100 for 100. Okay, 100 for 100. And in y-axis also, let's go for 100 for 100. Okay. So just lost in everything, and these are the some complex functions. So these are getting very complex now. So let me show you another one. Z power 3 plus 67 into z, not even 67, we don't need 67, we will just keep it z plus z minus 2, or let's have a simple one because we have to show that it's analytic everywhere and everything. So just insert and circle into this. So inserting a circle is nothing but you just go here and you just plot this z squared. Okay, z squared plus z minus 2, and you just plot this. You have a wonderful function like this in this so-called this domain of complex numbers, and you just can see how you will get really lost in this. And let's go for a line. So a line, this is the real part and this is the imaginary part. When you just get lost in this, you just have a small grid like this. When this grid goes small, okay, for example, for circle you have a chordioid like this. When this goes up and down, you can see the transformations. Okay, you can see all those transformations up and down. So you can see that the circle is being situated in this manner. So let me show you a proper way of plotting this. So for example, when I just substitute for z, I am just giving for this circle, I am giving uh, cos t. Okay, cos t for z plus, for percentage I is just a maxima syntax, you don't want to confuse with that, sin t. Okay, sin t, cos t plus percentage I is nothing but is an imaginary number. Now what you do is just you separate it into one real part and you just separate it into one imaginary. It takes all the pain from you. This software really takes all the pain from you. This is an open source. It exists before 1950s. It's a computer algebra system, and I have a wonderful software for this graph. Okay, graph pad1 grapher, which is a wonderful software for this, and I'm going to show you how this so-called Riemannian numbers is connected with this conformal mapping. Please wait. So you have this insert function and take the imaginary part and you just get over here, close this and take here and go to the y of t and you just paste it over here, and you just go to this real part and you take this real function and paste it over here, and you have some division symbols that should not show up. Okay, you just, because it thinks it's a math script, and you have a wonderful cardioid. Can you see when I just plot this function? Can you see it? Okay, you can see it. So when you just put a into cos t into sin t, you just get a wonderful function like this. Okay, these are the details so far I have given you. Okay, what about the zeros of this Riemannian hypothesis? Okay, what about the zeros of the Riemannian hypothesis? Can you please explain us with a very in a very visual manner so that we can understand? Okay, then me just as plotting it in a way. So let me get to you back. Okay, there are lots of software which deals with this, and there are lots of things to deal with this kind of thing. Okay, and first of all, I have to tell you that zeta function is not that easy to plot. For example, when you just put zeta zeta of 6 plus 7 percentage I, okay, yeah, so it is just giving a percentage I, and you just deal with it. And when you just take it as an real part or an imaginary part, it just bees in that manner. So, or you just convert it into a float, okay, you get this function. Okay, what is this zeta function? What does this have to do with this? So I'm just taking this zeta of z. So I'm just having this as zeta of z, and I'm just, what I'm doing is that I'm just going to the simplify. I'm just going to get the real part. It just has nothing to do with this. So for that, what we can do is we can convert this zeta into x plus, this is the Riemann zeta function, okay, percentage I into y, okay, and you just go over here, convert this into one real part, and you convert this into an imaginary part. Okay, you get nothing, and everything is very bizarre in this, and you can't do anything. Or you just go over here and differentiate, you won't get anything. But the real function, how it deals with this, is 1 divided by n power z. Okay, it is n power z. Z is a complex variable, or n power s. S is a complex variable. So now what I'm doing is that I'm going to calculate the sum. Okay, calculate the sum. So 1 to n, let it be 1 to n, and let this be, oh, okay, this is going to be a variable n, and this is going to be 1 to k. Okay, 1 to k. So let's plot. So this is the Riemann zeta function, and now what I'm going to do is I'm just going to plot, get over here, and I'm just going to differentiate. Okay, differentiate with respect to is z, okay, with one time, and you have this function. So you just see that it just shows up in a manner. Then for this function, z is the normal complex variable. So we are going to launch an Newton-Raphson method on this. Okay, so let's do it in this manner. So let's get over here and just copy this, and get over here and paste this, and copy this and paste over here, and you have a wonderful function like this, in which we can perform the Riemann zeta function. Okay, Riemann zeta function is Newton-Raphson method. So can I plot this in a software and see how it is being done? So it's very difficult. It is difficult to plot this function, and it's difficult to find the zeros. There are very special programs for this to do. Okay, I'll just tell you a very easy way to get this. So you just go to here, Riemannian, Riemannian hypothesis, zeros, zeros. Okay, Riemannian hypothesis zeros, when you just see, it nearly deals with these functions. Okay, these are the functions. So you have an imaginary part and everything. So I have told you a lot of time, how does this really matter. You should not find the trivial zeros, which is -2, -4, and -6. You just have to find the non-trivial zeros, and the non-trivial zeros are in this manner, that the zeros should be on this line, or it should be not on this line, it should be beyond this line, but after the critical step, but it could be on anywhere, but not this trivial zeros. Okay, so what does this really mean? So it is very important to everybody that these zeros really mean a lot, because the gap between these zeros tells the gap between the prime numbers. Okay, so far I have given you all these details. So let's plot this so-called prime number, sorry, so-called this imaginary, and this zeta function, and tell you the primes. So let me come over here, just delete this, and I have already made a video. This is only possible with this software. It could be also possible with another softwares, but I don't know. This is pad1.dk. This is a grapher which is available for plotting the Riemann zeta function and plotting it in a very good way. Okay, let me show you how to plot it in an easy way, because you cannot plot it with maxima, and you need to have a lot of computational effort to plot it. So I'm going to show you how to plot it easily and visualize the zeros of the Riemann zeta functions. So let me show you. Wait a minute. So friends, I will just tell you how to plot the parametric method of this equation. So let me just show you how to do that. So you have an equation like this. So let's get back to this equation, so called this Riemann zeta function, and let's copy this. And even Ramanujan's greatest mystery of this uh, uh, natural numbers convergence sequence is also in this. Okay, when you just you have only known that 1 2 3 1 plus 2 plus 3 plus 4 plus 5 is infinity, but you can prove that it is minus 1 by 12. So now what happens is that you just get over here, and you just, for z, no need to differentiate and get into the Newton-Raphson method. You just get over here. You can also use Jacobian methods of solving these equations in a 3D manner of Newton-Raphson method to find the zeros of a 2D function or 3D function. So now what we are going to do is, for z, I'm just going to do x plus percentage I am telling you again, it's just a maximum syntax for imaginary number. Now what happens is that you have an equation like this, and you just separate it into real part. So you can see this a tan 2. What is this a tan 2 and how to plot this? So again, you just get over here to this imaginary part. Okay, you have this. So these are the real and imaginary parts. You can see that automatically exponential function has something to do with this prime numbers and all those Riemann hypothesis. Okay, let's get back to that. So again, when you just go over here, and what I'm doing is that for x, what I'm going to substitute is, I'm going to substitute for x half 1 divided by 2. Okay, I'm going to substitute that 1 divided by 2. Okay, then what is this 1 divided by 2? Why are you telling this 1 divided by 2, and what does this need to do with this Riemannian hypothesis? So I am telling you this, you have a straight line like this, and all the zeros, as you can see, are within this. What they are telling, that all the zeros are within this, and the gap between this, so the first gap is between 3 and 5. Suppose first gap between the zeros is 3 and 5, and the next gap would be between 5 and 7. Okay, 5 and 7, these are the gaps between the prime numbers also. Okay, so far I have just told you all those details, and now what I'm going to do is, I'm going to plot these zeros. Okay, and I'm going to show you how. So these are the things I can show you now. So this is half, and for y I'm going to plot as t. What is this t? What does this t have to do with this? So let me show you. Actually, I have showed you in this already on this function of this explore math 3D. Okay, this is not an Riemann zeta function or anything. I'm just going to come here, conformal maps, and I'm going to just plot this. So you just assume this as a Riemann zeta function, and it is being a gridded map like this. And now what I'm going to do is, I'm just going to take an action of this. I'm going to draw a line. So this is the critical strip. Suppose you imagine this is a critical strip. It is being transformed into an parabola. But the real, what happens really is this. What happens really is this. You just get this. So this is the real part of the zeta function, 0.5 into t. So I'm just going to plot this, substitute for y, you substitute as t. That's a t. Okay, that's enough. Now what you do is just get over here, go to the complex function, get the real part. Oh my god, it's a huge function. Okay, so it's a very huge function of this format, and you get the imaginary part. Oh, how can I plot this? What is this a tan 2? Oh my god, I could not understand it. So I just have this a tan 2. You have, if a sequence, so you just have to take this. 1 minute, I'll just make a small adjustment. It doesn't have to do anything with this for so-called um, formula. Okay, Put the greater angle bracket, right, greater, put the left left greater angle. Okay, and it should be put the right, and I'll show you how to do this. Okay, so how to plot the A tan 2. Okay, okay, right, it's over here. So you just have to make an if sequence, and in that if sequence you have to plot it in this manner. Okay, this is the if sequence, and A tan 2 will be of this format. Okay, the A tan 2 will be of this format of x and y. Okay, so but in Riemann zeta function, what I'm going to do is I'm just going to copy this. I'm not going to mess with this all those very big equations, and I'm not going to mess with anything. I'm just going to show you how to plot all those zeros of Riemann zeta functions. And let me tell you this, I'm not going to deal with this exponential on everything, because it's very complex to convert it into a polynomial or a Taylor series and then switch it on and run it. So I'm just going to just make an Riemann zeta function, which is already available in the software of pad1.exe. This is a very wonderful software. Okay, this I'm going to plot. As you can see here, it is real of zeta 0.5 into t. And again, I'm getting over here. I'm just going to here and copying this and just pasting over here. So this is 0.5 into plus t. It is Riemann zeta function's imaginary part. So let me show you again. So this is the function. So it is for x of t, you're just plotting real part of the 0.5 into t, and y of t, you're plotting this. So again, you just get over here, and this is from 0 to 34. Okay, this is from where is from 0 to 34, which will be visible for you. Okay, I'm just going to do this. Oh my god, what happened? Okay, nothing just happened. It is not showing up. I think, wait a minute. 0 to 34, and what about this? Okay, 0 to 34 of 1000, real and imaginary widths, and just plot it. Wait a minute. Okay, dear, I just made a little big mistake. I just have to on the complex settings. So just go over here, go to the edit, go to the settings, and just do calculate the complex numbers. Then just get over here and just insert function, then just get to x of t, y of t, and just go here. And you first, what you have to do is you have to copy the real part of the zeta function. So this is inbuilt with it to just find the real and imaginary. So you don't have to just get with all those things. It does lots of good functions in complex numbers. And the next would be the imaginary part. Okay, just copy this and get over here and then just paste this, and from 0 to 34, or else you can just go to 0 to 50 or anything. Oh my god, you have a wonderful Riemann zeta function. This is what you see everywhere in this so-called what to say, so-called so-called your internet and everything. So let's plot the zeros one by one. So let me go to the sequence. Okay, let me go to the sequence now and get over here. And what is the first thing? So the first zero, it is the critical strip, and the first zero is half plus 14.13. Where is it? Okay, it is 0.5. It is 14.13. The zeros of Riemann zeta function. Okay, it is very, it's very small to see. Okay, and just get over here, and size of the thing. So it is 0.5 into, so the zeros 14.3. So in y-axis it is 14.3. Okay, it is over here. So I think I have to increase this function to 50. Okay, 50. Because why I am telling is that this is imaginary and this is real. Okay, So the first thing is not very clear. So the zeros are all within the critical strip. And what about, let's go to at least up to 500, okay, so that it just reaches over there. Still it is over here. So then let's go to 1000 or 10,000. It just takes some times to plot. Okay, oh, it is still there. So let's stop with 50. Okay, let's stop with 50. So in order to plot every zeros, you need to have some details on this. So let me show you all those zeros one by one. Okay, so the first thing I got from the internet. Okay, the first thing I got from the internet. Okay, so these are the zeros. So next diagram I will show you. Okay, and over here, so they're just telling you that every zeros, as you can see from here. So when you see, actually the first zero is over here and the second zero is over here. Okay, the first zero is over here, A, B, and some zeros are even at the upon the curve. It is upon the curve. Okay, it is even upon the curve, and some zeros are in the line, on in the real axis line. Okay, so this so-called real, so this called this is 0.5 into 14.135i. Okay, 0.5 into 14.13i. So we have to calculate that, and we have to find the zeros exactly on that curve. So how to do it? So let me show you. Okay, so they are telling that you have to put 0.5 into 14.13. So just get over here and you have to calculate the sum. And in here what you have to do is you just go over here, you just plot from 0 to 34, just 34. Okay, 34. So not 14.13, 14.13. Okay, let's go there. Oh, it's going to take a long time. I'm sorry. So let's go to 0.1. So this is a calculator that is available over there. Okay, so you just go down and you can see that for 14.1 there are some 0.47 or something is over there. So let's go even beyond that. Okay, so what happens in 14.13? So 14.13, the number gets very small. Okay, the number gets very small. So for 14.13, it is for x of t 0.006 and 006 minus 0037. Okay, on the curve 0.0037. So you just have to close this 006 and 0037. So let me get here and you just copy this. Okay, copy it, close this, get over here and then just paste this. Okay, something is over here, so it is not nearly to that function. Okay, it's not nearly to that function, but the real one is that when you just plot it, you get it over here. It is actually over here what they are showing it over here. Okay, I could not plot it really well. Okay, so when you just plot it over here, so after this I'll tell you the zeros. I'll tell you all the zeros, how to plot this and everything. So the sum of the f point, what you can see here, what you can see actually the zeros of the f point. So A, B, C, D, G, E, F. So you have a 0 over here, it is actually over here. So some zeros should be over here. If you find any zeros in here or here or here, you can win that money, I think so. Okay, I could not be clear at this point. So this everything is only within this curve. Okay, everything is within this curve. So actually what happens is that the point whatever you find, suppose you find a 0 here or here, you win the 0. But if you find every zeros would be separated in a manner that within this curve. Okay, so this is what they are showing it over here. Okay, this is what they are showing it over here. Everything is within the curve. Okay, everything is, okay, wait a minute. So they are telling that everything is within this curve. Okay, so really what happens is that you see f is within this curve, e. So all these so called this complex functions, no, this half into t is just over here. Okay, so you just have it over here. So this f is within this curve. So there, what's the big deal is nothing but when you just have, you have f is over here, so f is the 0 over here. Okay, and a and b are all within this curve, but they are separated, they are just separated in a manner that but they could not be here or here. These are special critical points. Okay, trivial non-trivial zeros you have to find. Okay, but everything should be within this curve. Okay, but this just crosses the 0 often and often and often and often, but it doesn't matter. But every 0 lies on this critical strip. Okay, but if you find a 0 on here or here, you win $1,000,000. Okay, so this is the way you plot this so-called Riemann zeta functions. So this is the way. Only thing is that you can find zeros anywhere. So the point what they are telling is you have a critical strip in which these zeros half into 21.02 of I and everything is being plotted in over here. You have these zeros, but these zeros are all within the strip. Okay, these are, they are telling that you have the critical strip and every line is, every point of 0 is over here. If you just find a 0 over here or here which doesn't lie within that critical strip, you are the winner of the uh, millennium prize problem. So thank you. So these are the details so far I can give you, and at last let me show you and great explanation of what is conformal and what is non-conformal. I am telling you again, non-conformality is the most bizarre, most different thing what you are going to deal with. It is not like that. Okay, it is just, conformality is just a bizarre one. Okay, let me show you a small example. Okay, why I am dealing with this AutoCAD and what does this have to do with conformality and non-conformality? So I am telling you again, so let me show you that software again about this conformality and non-conformality. So let me get to the desktop and go over here and match softwares and go to the 3D Math Explorer. And getting over here, let me show you what is conformal. What is conformer and what is non-conformal. So you have this 1 by z minus a. So what happens is that when I just zoom this, okay, now you can see that these thing and this point is being mapped over here. Okay, this point is being mapped over. This is a conformal, you have to understand. So this region, what you are seeing here, this region is being mapped to this region. It is being transformed. Okay, it is being transformed. Okay, now what is the deal? So conformal says that the area, so this internal area what is inside and the internal this area inside is equal. And not only that, the what you are seeing here, the angle, suppose this is 90 degree and this is suppose 90 degree. How could this be? This is somewhat deformed, no? But when you take an curvature point of view, when you take this moving trihedron, you can see that this angle will be equal to 90 degrees everywhere. So this is the conformality. Okay, dear. We could not prove the angles are equal, but how can a area preserve itself? How can a area preserve itself, and how can it be done? So let me show you an example which is very 2000-year-old examples, which Euclid did not feel about it. But after I had an idea, so this could be a point where the conformality exists. Okay, so let me show you that. So I'm getting over here. I'm just drawing an arbitrary. Okay, I'm just drawing an arbitrary rectangle, and you have a very different kind of rectangle. Okay, so I'm just playing f8. So just put it like this, and you just take this and get rid of the f8, and just draw this and put this. Now what I'm doing is that I'm trying to do one simple procedure. So in here I'm just drawing a straight line. Okay. Okay. Now I'm just joining it. Join, join. Okay. I'm just joining this line in order to find the area. So let's join all these things. Right. Now let me find the area. Oh, for example, mass prop. This is the formula to find the area, center of gravity, and everything. Okay, mass prop. And just hit enter. Okay. MASS, mass prop. And just hit this, and you just hit the enter. So it is not a region. It is telling that it is not a region. So you just, yes, region. So you just paste this, and you just give it an region syndrome. Okay, you can't see that when you can travel from here to, okay, you can travel from here to here, and you can see that region format. Okay, now let's do MASS, mass prop. So let me give the mass prop, and I'm just hitting this area and just hitting enter. And you are seeing that the area is 38,4755. Okay, 38,4755. You note this. So I am just finding the area for this. So now I will show you how conformality even exists in geometry. So you just take this and take this line. Let me come here. Yes, and not this. So just take this and draw. Take this, get rid of this f8, and you just draw this. Okay, and draw an uh, line over here. Now what I am asking you is that I am just picking this area out. So I have just deformed it. I have just deformed the triangle to this extent. I don't know why this happens, but the proof of conformality is even before 2000 years. I feel, I don't know whether I am wrong or correct, but this is there. So what I am telling you is that I am going to copy it. CO. Hit enter. And not this one, I'm sorry. CO. And what I'm telling this, that I'm extracting this rectangle. Okay. And getting it over here to Control V. And I'm just pasting it over here. No, not this. So you just have this move, MOVE, move. And first select the object, OVE, move. So first select the objects. So this AutoCAD is nothing but it is just an geometry software. Okay, every CAD. So when you're just moving it here from here to here, so this is what I am telling. I'm going to confuse you now. I'm going to throw a chaos at you. Okay, and I'm just connecting these two things, and as you can see, the base are the same, but the thing is deformed, the triangle is deformed. If I tell you, is this line what I am drawing, is this line and this line, are they equal in length? Are they equal in length? No, they are not equal in length. Then how the area is preserved? So let me show you the proof. REG, so you have this region and you just hit this and you have this. Now you see that mass prop. I am not fooling you. I am not using any gimmicks over here. Okay. So you just hit this. You can see that it is 38 units, tens, hundreds, thousands, 10,000 lakh. It is 3,84,000 in area. So this mass prop, then you just hit enter, you can see it will be equivalent to this also. You can see that same area is over here. I'm not fooling you. I'm not really fooling you. You can see it. Whoever knows the CAD will also knows this. Okay. No matter if the triangle is deformed from the straight line, it just turns out to be an equal in area, but the angle is somewhat different. So this is what is being shown in this non-conformality conjugate z of a into z squared. You can show here. What I'm telling is that is so simple. When you just get over here, for example, so what they are telling is that when I am just integrating the area within this and this, you just integrate it. This area is not equivalent to the area over here. Okay. So this is what I am telling. And the next thing is that when you see here in this conformality, this both are, even though the shapes are different, they have the equivalent area. So this is the chaos I am throwing at you. So you deal with it. And I have given you all the details about the Riemann zeta function and everything. And this is the conformal map, non-conformal mapping thing. Okay. So thank you for listening it for more than 1 hour. Okay. I have made this video possible because I could not plot more of the zeros and it was not really able to plot it. But I can give you the actual idea what you can do. Okay. I can give you the actual idea what you can do. So these are the main details of this conformality and non-conformality and analyticity of functions can also be dealt with this. Okay. Okay. So these are the details so far I can give you. So you have to follow our channel very closely. So I have made this video in English because more of the English audience are more interested in this Millennium Prize problem and they just wanted me to do this video on this manner. Okay, I have just showed you lots of softwares and lots of details on this Riemannian functions, Riemannian hypothesis on this critical step and the conformal and non-conformal thing. So it is an 1 hour video, nearly to 1 hour. Okay, so you should just digest all these information in your head and you can just it is not about winning the prize, it is just an intrinsic beauty of mathematics that you have to digest within yourself to just see how mathematics in itself it has all the visual concepts in it. So visual mathematics is sometimes very misleading, but even though it is so beautiful and it is so very strange in nature that it could not really pinpoint a way of accuracy or this is what I'm telling about fractals or anything. Loss of perfection is not a mistake. Loss of conscious is a mistake. This is a proverb that I created in my own self. So loss of perfection is not at all a mistake, but loss of consciousness is a mistake. I think everything is inbuilt into the what they say. I can even take you to some other things. So the eternal law is different from preserving law. Okay, so these have very deep implants into this computability theory and all those things. So even in prime numbers and everything, so they have to find the roots of everything. So no matter how far you travel in future with advanced technology, no matter you have proper tools of mathematics, you are not in an advanced stage of science or anything. Okay, because science is just an approximate, and I can tell you that science can only predict, or it can only show you some approximate values. It is only accurate to certain extent, but still I'm telling you, there are lots of hope in mathematics to advance yourself. So science is just an approximate, but math or mathematics is absolute. Thank you. Please like, share and subscribe.